All right, hi everybody. Running a little late because my last class ran late, and let me just find your stuff. So just finishing up some stuff for my honors chemistry class, and let's go ahead and look at what you guys had. Now I know my last assignment I think I gave you guys was just that reading, right? And I don't think we talked about any of this stuff from the last class. So I believe what we're going to do today is we're just going to basically just talk about this homework assignment, okay? And you guys should have turned it in by now, but if you got some stuff wrong, no big deal. My whole goal today is just to make some sense of the homework so that you guys can understand the homework as much as possible, and then that's it, all right? And then for your homework today, I'm going to give you guys some reading to do and some videos to watch, but no new paper assignment, okay? Hopefully it doesn't mean that you think, oh, okay, that means I can do nothing. No. So I will give you guys some paper, some book stuff to read, papers to read, and videos to watch. Shouldn't be too long, but I want you guys to watch that so that on Monday, when I talk about some new stuff, you're not all super confused, okay? So today, let's just get into the homework that you guys had to do. And before we get started, I'm just going to tell you guys, so we are not going to have a test before the break, but we are going to have a quiz, okay? So and I haven't graded your test yet. I'm so sorry. I've been working on some other stuff, and probably like tomorrow, I'm just going to sit down and just do nothing but grade. So I'll have your test graded tomorrow sometime, all right? So yeah, sorry about that. I hate being behind in grading, but you know, it is what it is. So here we go. Quiz. I'm shooting for Tuesday for a little quiz, just a little 10-point quiz. And the main thing that will be on the quiz will be this stuff talking about maybe identifying Arrhenius acid and bases and your Bronsted-Lowry acid and bases. That's going to be the main stuff on the quiz. Once again, it's going to be open notes kind of thing. So you don't need to memorize anything, although I do say up here, memorize. You know, there's no point, although I'd like you to be familiar with the stuff, okay? All right, so hopefully you guys did the reading. And up here, let me just talk a little bit about these acids. When you're actually in the lab, it's nice, and when we're talking about stuff, it's nice to know how to name some acids. And I've just broken it down to probably the 5 most important acid names that you guys should know. And so it'd be nice if you could just go through this quiz at one time just to familiarize yourself with these acids. But again, all your tests and quizzes will be open notes, so there's no point in really memorizing them. But I would try to maybe just go through the Quizlet one time just for fun to learn this stuff a little bit. So, without further ado, let's jump into number 1 here. What is an Arrhenius acid and what is an Arrhenius base? All right, Arrhenius was one of the first important guys to really talk about acids and bases and kind of think about what they really were. And he said this, right? An acid is going to be something that is going to give H plus to a solution, okay? Or it's going to increase the amount of H plus in a solution. The base, according to Arrhenius, is going to be something that's going to give OH minus to a solution. Or more accurately, to increase the amount of OH minus molarity or concentration you have in a solution, okay? So an acid is something that gives H plus, and a base is something that gives OH minus. And the way that we can identify an acid or a base based on Arrhenius' definition is simply this. The acid is going to have an H plus, I'm sorry, actually you won't always see that. The acid will have an H in the front of the formula. Now, it's not always the case there are sometimes somebody's going to write something with the H that's going to be somewhere else in the formula, but anytime I give you guys the formula, I will make sure that an acid will have H in front of the formula, okay? There's only going to be one exception to that, and it's not an exception, but it's more of an exception to the converse of this, and that is this, that H2O, although it has H in front, is not an acid, right? H2O, and that should be a common exception that you guys realize, oh, H2O, that's not an acid, it's not a base, it's just neutral, okay? So everything that has an H in front of it will be an acid according to Arrhenius, except for water, okay? All right, everything that has an H in the front of the formula is going to be an acid except for water. Base, how do we identify a base? A base is going to be something that's going to have a hydroxide in the formula. So it's going to be something OH, okay? Now, there are some exceptions to this too, but you're not going to really see those exceptions. And those are going to be, let's say, your organic alcohols, but I'm not going to show you guys anything like that, okay? So for the most part, it's going to be your base is going to be an ionic compound, where this X is going to be, let's say, sodium, potassium, lithium, calcium, magnesium. For the most part, it's going to be some metal here, hydroxide, okay? And that's going to be what an Arrhenius base is. And so by simply looking at the formula, you should be able to identify an acid or a base, okay? So let's go through these for number 2. All right, number 2. The first one does not have an H in front, and it does have a hydroxide in it. So right away we're thinking, okay, that's a base, okay? The next one has an H in front, and so that should be an acid. The one after that has an H in front also, and that is an acid. This is hydrobromic acid, and this is nitrous acid, okay? Some less common acids, but they're acids nevertheless with an H in front. Over here, potassium bromide. I do not see an H in front, and I do not see a hydroxide. So according to Arrhenius, this is going to be neither. And we should expect that because potassium bromide is just like sodium chloride. It's a simple ionic compound without hydroxide in it or anything like that, okay? So that's neither. The next one, there's no H in front, but there is an OH right there. This is barium hydroxide, and so we're thinking that should be a base, okay? Now, H2O looks tricky, but you guys know water, right? We all know that water is just a neutral compound, so we're going to say that is neither an acid nor a base, okay? So, questions on these. You will have a question like this on your quiz. One of these types of questions should be an easy type of question, okay? So make sure you're able to do this, identify an acid or a base according to the Arrhenius definition, and keep in mind, I might throw in some of these neithers in there too, okay? So, next up, if there are any questions, just ask the question, otherwise I'm gonna go on. Next up, what's the difference between ionization and dissociation? And in order to answer that, I'm going to go ahead and jump down here to numbers 4 and 5 and kind of show you what this whole ionization versus dissociation thing is. So for number 4, write the balanced chemical equation for the ionization of H2SO4 in water. There's actually a couple different possible reactions that we could write for that. But let me do it this way. And I believe your book has some of these written down. So this is sulfuric acid, and so we could write it like this. H2SO4 reacts with water, and it's going to make, so is that the H is going to stick to the water, and it's going to make H3O+, and so this is going to lose one H, and that's going to make HSO4 minus. But you might recognize, well, there's still an H in front here. And so this can happen again. So you could have written this reaction, or you could have written this reaction instead. H2SO4 plus water is going to make not one, but two H3O plus S. Sorry guys. It looks like there's a little bit of a technical difficulty there. We just went out for a little bit. I don't know why this is happening. But anyway, we're back on. So let me first say this. You could have written either one of these reactions. This is ionizing one of the hydrogens, and this is ionizing both of the hydrogens of sulfuric acid. Okay? So the question is, can an acid have 4 hydrogen atoms? It is theoretically possible, but the real answer is actually it's going to be pretty rare. It can actually let me say, it can happen, I suppose, for fairly large organic molecules that you can have more than you can have 4 or even more hydrogen atoms. But you're not going to see that for any kind of small molecules like this. It'll be fairly large molecules, okay, where you have a whole bunch of those possible acidic hydrogens, all right? So nothing that you guys see will ever have 4 hydrogen atoms, but it is possible. Okay, so both of these, either one of these is certainly a possible reaction that you could have written down. Let's jump down into the base, and then I'll come back up and answer number 3 here. The balanced reaction for the dissociation of magnesium hydroxide, that's going to be MgOH2, which is not very soluble, right? It's a alkaline metal hydroxide, which is not very soluble, but you can dissolve a little bit in water. So when it dissolves, it makes Mg2 plus and 2 OH minus. So now we can kind of get to and see what the real difference is between these. But I got a question here. How do we know what equation you want on the test? If I were to ask this question, either one would be fine. Okay? Sometimes there might be more than one possible equation, and either one would be fine. Okay? All right. So when we look at these and we say, okay, this is ionization and this is dissociation, we can see a couple differences. The first difference is this. This magnesium hydroxide, that is an ionic compound. It's made out of ions, all right? Sulfuric acid, however, is not. This is a covalent compound. Okay? It's got all nonmetals. It's a covalent compound. It acts like a covalent compound because it's a liquid, not a solid. This is an ionic compound. Ionic compounds tend to be solids, high melting points. This is definitely an ionic compound. And so that's the first difference between these two. The second difference is, well, when we dissolve an ionic compound in water, all it's doing is splitting up. It's just the 2 ions that are dissociating or splitting up. Okay? So that's a simple splitting up of the ions. And the ions are already there. But in the covalent compound doesn't have ions to begin with, so the covalent compound is actually reacting. All right? So that covalent compound, when it's ionizing, it's a chemical reaction with water. So it's reacting with water to form the ions. And so I noticed that you guys are having a little bit of a problem with the signal here, with the live stream. If you guys want, you can just click out and come back later. And once this uploads to YouTube, it should be perfectly fine and glitch free. So sorry about that if you guys are having a little bit of problems with the signal there, with it going off and on. All right, so coming down here, any questions about this? Ionization, dissociation, all that kind of stuff? All right. So we have the last thing here is about polyprotic acids and identifying these polyprotic acids up here. A poly, which is many, and protic, well, what in the world is that protic coming from? Protic has got to do with protons. And what do protons have to do with all this stuff? if you look at an acid, the distinguishing characteristic of this acid is this H+. An H+. But an H+, remember, a hydrogen is simply a proton and an electron. All right, one proton, one electron, that's a hydrogen. But if it's an H+, that hydrogen atom has lost its electron. So therefore, H+ is a proton, right? An H+ is a proton because it's just a hydrogen that's lost its electron, and the only thing left is a proton. And so when we say a polyprotic acid, we're saying that it's got many protons or many H+, or more than one H+. So polyprotic acid is any acid that has more than one H in front. Okay? That's a polyprotic acid. One more thing I should say about this is that I'm going to talk about H+, but I'm going to use them interchangeably. So when you have H+ that's dissolved in water, the H+ is going to be in the form of H3O+. H3O+. Sorry about that. And the reason for that is this H+ is so positively charged, so reactive. It so much wants electrons that it's going to stick to something. And when it's dissolved in water, the H+ is always going to stick to a water molecule, right? So you have H2O that has 4 electrons, non-bonding electrons. And then you have an H+ that's going to be dissolved in water, and right away that's going to form a bond there between the H+ and the OH-, and it's going to be something like this. It's just going to look like OH, H. It's going to bond there. You'll still have one lone pair of electrons, and this whole thing, this H3O+, is going to have a positive charge. Okay? So sometimes I might say H+, sometimes we'll say H3O+. Keep in mind that those two things are really the same. Okay? All right. So last on this page, we're going to identify all the common acids that are monoprotic, diprotic, and triprotic. We're going to go up here. So let's just scroll this down, come over here, and all we need to do, super easy, all we need to do is just look at the first thing here and see how many H's there are. If there's one H, like in hydrochloric acid, that is monoprotic. If there's two H's, like in H2SO4, that is diprotic. Di means two. One H, monoprotic. Three H's, triprotic. So phosphoric acid is a triprotic acid. All right? Triprotic. Carbonic acid, there are two H's, so that should be a diprotic acid. Okay? All right, you guys still with me here? I know there's only 5 of you guys. There must be some kind of technical issues there, so I'm sure the rest of you guys are just going to watch it later. Sorry about the technical issues. Okay, is anyone else having an issue with the video? I had an issue earlier, but it's gone now. And that was, it just got stuck at one spot and then it restarted. So hopefully you guys, the rest of you guys are okay. But does anybody have any questions about the chemistry? All right. So let's go on. And that is, this next page is all about another definition of acids and bases. So the first page is Arrhenius, second page is Bronsted and Lowry. All right? So sorry guys if yours is just loading. Yeah, you might just have to come back later. Real sorry about that. All right. What is this Bronsted-Lowry acid and base? The Bronsted-Lowry acid and base, the main difference in their definition is this. Bronsted-Lowry acids, bases, they always come in pairs, right? You can't have an acid without a base, and it's always dependent for a reaction. So you can't just have according to Bronsted and Lowry, you can't just look at some chemical and say, okay, that's an acid or that's a base. They're going to say, well, actually, it depends, right? Something might normally act like an acid or normally act like a base, but sometimes it might act differently, okay? And so a Bronsted-Lowry acid and base is going to have, is going to be dependent on the reaction itself. It depends on the reaction. So whether it's an acid or a base is going to depend on what it reacts with. Okay? So back up to the actual definition of your Bronsted-Lowry acids and bases. Bronsted-Lowry acid has a very similar definition, but it's going to be something that is going to give away an H plus in a reaction. Okay? And the Bronsted-Lowry base is now going to be a little bit different from the Arrhenius definition. It's going to be something that's going to accept an H plus in a reaction. Okay? So our definition of an acid is very similar, but the definition of the base now has got to do with, okay, the acid is going to give the H plus and the base is going to accept the H plus. And so we're going to forget about the OH minus. You don't have to have OH minus to have a base. It's going to be all in terms of, well, what's this H doing? Is it going? Where is it going? It's going from the acid to the base. So down here, and number 10 is probably going to be the hardest question in the whole, homework, but it's going to be very, very important. And so hopefully you guys can see what's going on. So I'm going to go through this. I'm going to go through all of these problems, but we need to keep in mind what that Bronsted-Lowry acid-base definition is. So we could probably, at the first one, just identify them based on our Arrhenius definition of acid and base. Right away, we look at this. That's got an H in front, so it's probably going to be our acid. That looks like it's a base. It's got an OH minus there. And we can go ahead and just start with that. Okay, let's start with that kind of definition and say, okay, that's fine. This is our acid, and this is our base. But we also want to see, okay, what happens to the acid after it loses H plus? What happens to the base after it gains H plus? And that's going to be what our conjugate acids and conjugate bases are going to be. The conjugate acid is going to be the base after it gained H plus. Why do we call it a conjugate acid rather than conjugate base? We call this a conjugate acid because once the base gains an H plus, it's now going to have the H, so it's going to look more like an acid. The conjugate base, is what? It's the acid after losing H plus. Okay? So what do I mean? Let's look at this base first. The base has got this OH minus there and is gaining an H plus. The acid has an H and is giving the H to the potassium hydroxide. And when it gives the H to the potassium hydroxide, it's going to form, so H plus and OH minus, that's going to turn into H2O. So right over here, this base is going to turn into a conjugate acid. They are a pair, okay? So this turns into the conjugate acid. The acid, in turn, is going to lose that H plus. When it loses the H plus, it's going to turn into Br minus, and the Br minus ends up right here. So this is going to be our conjugate base. All right, these two form another pair. So you have an acid-base pair, and you have an acid-conjugate base pair, and you have a base-conjugate acid pair. So this whole concept can seem kind of confusing, but I think we can make a little bit more sense of it if we just realize that the potassium isn't doing anything. So what I want to do is I want to rewrite this whole equation above and think about, well, what's really going on? So let's forget about the potassium and look at what this whole reaction is up here. So that's going to be OH minus, right, removing that potassium, plus HBr is going to make, removing the potassium, Br minus plus H2O. Okay? And so when we look at that, we look at, okay, here's our acid, here's our base. What's going on is we're taking that H and moving it from the acid to the base. And what's left is, here is that acid which is lost, it's H plus, and so that's going to be the conjugate base. And then that H is going from the acid to the base, and so the base is now turning into H2O, all right, which is going to be your conjugate acid, okay? And so keep track of what is going on with this H. Keep track of where the H is and where it's going from, okay? The thing where the H starts, whatever is losing the H is going to be your acid, whatever is gaining the H is going to be the base. And then you can look over here to figure out, okay, what is it? What is the acid turned into? Is turned into a conjugate base, okay? So please take some time and make sure you can follow the H for this first one, because the first one is going to be a little bit simpler than the next one. Let's go down here. The next one, we have, there's a problem when we look at this next one, we have actually two acids, right? According to Arrhenius, this is an acid and this is an acid. This is sulfuric acid and this is nitric acid. Well, what happens if you combine two acids together? They can actually react with each other. And one of them is going to act like a base and the other is going to act like an acid. This is actually a very important reaction which is used for the manufacture of a lot of different things, but specifically it's used for the manufacture of your nitrated explosives like TNT, okay? And so let's see, we've got sulfuric acid and we've got nitric acid, and one of them is going to give up its H and the other one's going to accept the H. So we have to look over here. The sulfuric acid has turned into HSO4. So in that process, going from here to here, that sulfuric acid has lost an H. Here it has two H's, here it has one H, so it has lost an H. And the thing that loses an H is your acid, which means this must be your conjugate base, okay? And let's verify that over here. We have HNO3, which looks like an acid, but notice the HNO3 is turning into H2NO3+. So going from here to here, it has gained an H. And so therefore, the thing that gains an H is your base. And the thing that is the base after it gains an H is your conjugate acid. Okay? So we can see that it's really, really important for, according to Bronsted and Lowry, to look and see where is the H going. Okay? The thing that loses an H is your acid. The thing that gains an H is the base. All right, let's continue on. We have phosphoric acid reacting with sodium oxide. This one looks a little bit weird, but again, we're going to ignore the sodiums. Just like we ignore the potassium over here, we're going to ignore the sodium. We're going to see, okay, what's going on. Clearly, because this one doesn't have any H's and this one does, that's going to make this problem a little bit easier, okay? Because if this one starts with H, this has got to be our acid, okay? We don't even have to worry about anything else. The one that starts with the H is going to be your acid. And let's watch. As H3PO4 here turns into Na3PO4 here. The H3PO4 has lost all three of its H's, and here this is going to be your conjugate base. So we follow the PO4. PO4 here, PO4 here. Here it's got H's, here it doesn't. So this is your acid, and this is your conjugate base. Which means that, of course, this other one has to be your base, okay? And so the base is going to be the thing that's receiving the H. And specifically, it's not going to be the whole thing. We're going to ignore the sodium, and really this Na2O, that's sodium oxide. Oxide is O2 minus. And so this O2 minus is going to receive H's from the phosphoric acid. It's going to turn into water. This is going to be your conjugate acid. Notice that it seems that water very often is a conjugate acid. And so you'll find water to be a product in these acid-base reactions quite a bit. Okay? Once again, we're going to see another, look at that, we have another water down there. Probably that's going to be our conjugate acid. But let's actually look at the reaction first. Okay? Once again, this one's a little bit easy. I like the second problem because it's tricky, okay? It's hard. But this one is going to be easy because, once again, we have only one thing that has H in front. So that must be our acid. And we notice, okay, we're going to follow that carbonate. We have a carbonate here that's going over here. And so this acid, after it loses the H, turns into the conjugate base. Okay? And the other thing must be your base. The barium itself really isn't the base, it's the hydroxide here. So the hydroxide, the barium hydroxide, the hydroxide is going to receive H's from the carbonic acid. When it receives H's, it's now going to turn into water. So this is going to be, once again, our conjugate acid. Okay? Moving right along, we're going to find that not everything always looks the same way. You don't always have something that has an OH minus in it. And so here we have sulfuric acid in NH3. Although NH3 has a bunch of H's here, they're not in front. So we're thinking, oh, probably it's this one with the H in front that's going to be our acids. But let's make sure and see when H2SO4 goes over here that, yes, indeed, this sulfate, the SO4, has lost two H's. So this is our acid, and this is our conjugate base. And what has this NH3 done? The NH3 is NH3 here, and it turns into NH4 plus. That means it has gained an H. So this is our base, which is gaining an H, and it turns into the conjugate acid. Let's continue on. Two more to go. NH3 here, and H2O here. So what's going on? So neither one of these would normally be classified as an acid. So we need to look carefully and figure out, okay, which of these two is losing an H? Okay, which of these two is losing an H? So we find over here NH4, well, that has just gained an H, right? Going from NH3 to NH4, that's gained an H, so that's not what's losing an H. It must be the H2O. H2O here has two hydrogens, OH minus has one hydrogen, so this is your acid, and this is your conjugate base. Here you have NH3 going to NH4, so the NH3 is receiving an H, so this is your base, and this is your conjugate acid. Okay? Last one. This one looks really, really weird. What in the world is going on here? We have an N3 minus and water. Well, because the N3 minus doesn't have any H's on it, we're thinking, well, it probably cannot possibly be an acid because this one here has H in front and this one doesn't. So even though it's water, that's probably going to be our acid. Let's verify, okay? The H2O turns into OH minus, so yes, indeed, this is our acid, and this is going to be our conjugate base. Okay, the water has lost an H and turned into OH minus. What has this N3 minus done? The N here has no H's, and the N here has three H's. So this is our base, which is gaining H's and turning into our conjugate acid. Okay? So I know there's a lot of problems. You are going to have to do something like that on the quiz. I'll give you guys probably just one of these types of reactions. And so make sure you're able to solve a problem like that for a Bronsted-Lowry type thing. Last up, we have a couple minutes left. And so the last thing I'm going to do is go over amphoteric. You guys should have read about amphoteric in your book. Amphoteric simply means that something can be It's something that's amphoteric can be both or either an acid or a base. Okay, so something that's amphoteric can act either as an acid or a base. All right, and so my first question is, well, why is water amphoteric? Because water can sometimes act as an acid and sometimes act as a base. And so we go back over here and we look that, well, in this case, unfortunately, in both of these cases, acid is acting, or water is acting as an acid, but sometimes water can act as a base. And where have we seen that before? Let me turn this whole page around. Oops, nope, don't need to. It's on the other, it's right over here. We've seen water act as a base right here, right? In the sulfuric acid reacting with water to make H3O plus and HSO4 minus. In this case, this is your acid and water is your base, okay? Because water is receiving an H to turn into H3O plus. And so in that case, water is acting as a base, but in these cases, water is acting as an acid. And so water is amphoteric because it has, because it's able to act as both an acid or a base. And then let's identify one other chemical. We can look at this and you can find, I mean, there's a couple different examples, but here we have NH3 is acting as a base, and we have NH3 here that's a conjugate acid, right? Which means if we did this reaction in reverse, NH3 can act as an acid or can act as a base. Also, we have up here nitric acid, right? Nitric acid here is acting as a base, and normally nitric acid acts as, well, an acid. So a lot of things can actually be amphoteric. That's not something terribly special. A lot of things can be amphoteric, right? And there's really two things that they need to be amphoteric, at least amphoprotic if you want to be real technical about this. And that is they need to have an H in front, or not even in front. They need at least one H, and they need to have at least one or more lone pairs. But you're not going to have to really, that's not going to be super important for you guys. You're not going to have to be able to identify things based on that. It'll just be something, you know, you might see a couple different reactions and be like, oh wait, there the chemical is acting as an acid, there the chemical is acting as a base, and that's about it. Okay, so you don't need to necessarily, like I give you HNO3 and you say, okay, is that amphoteric or not? That's not the kind of question I'm going to ask. I'm not going to ask that kind of question, so don't worry about that. This, number 10, is a super important question that you're going to have to do on the quiz that you're going to have next week, so Tuesday-ish. And then also number 2. So number 2 hopefully should be easy for you guys. Number 10, a little bit more challenging, but you will have a problem like that. So class is now over. Do we have any questions remaining? Anything you guys want to ask me before we sign off for the weekend? If you're wondering about your test, I'm going to try to grade that tomorrow. So sorry about the little wait for your test grades and all that. But yeah, so that's it. Have a great and wonderful weekend. And sorry about any kind of technical issues you guys are having. It could be your own network or it could be Google's network. My network is working pretty well. All right, can you do some Lewis symbols? I could do some Lewis symbols, not very related to what we've been talking about here today. But if you can ask me a specific example, I can show you guys something. Like for long molecules. Do you have a specific question? If you give me a specific question, I could probably answer it. Do you have anything in particular you'd like me to go over? And the thing about long molecules, let me just say this while I'm waiting for your specific example. The thing about long molecules is that if you just give me the formula, I couldn't really write down the Lewis diagram or the Lewis structure of the thing because there's probably many different possibilities. Okay, and those different possibilities are going to be a bunch of isomers. Okay, and so if you're interested in that, let me just get another sheet of paper. And so for my class, if you guys, we're all done talking about acids and bases. I'm just going to answer this question, and then we'll be signing out. But let's talk about that real briefly. Let's suppose you have something like just C5H10. There's a whole lot of different molecules that have this formula. Okay, a whole lot of them. And in fact, let's do something a little bit simpler because of all the different possibilities for that one. Okay, let's try something like C4H8. Okay, and this is true for organic molecules in general. You cannot tell me what the formula, what this thing looks like just from the formula. Okay, so why is that? There's a whole lot of possibilities. So C4H8, it could look like this, and so let's do C, 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 C. All those C's could be in a line, right? And because our degree of unsaturation is 1, right? You have 8 hydrogens for every 4 carbons. We're going to have a double bond in there somewhere, right? So it could look like this. And let me put this up here. So this is going to be H, 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 H. So that could look like that. So that long molecule could look like that, right? Where we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, 4 carbons. But you could write this, this double bond anywhere, really, okay? So I could put the double bond C, C, double bond C, C, and it could look like this, okay? There's really so many possibilities even for this one simple molecule. Okay, those are structural isomers, or we could even have a branch in this, okay? And so I could have C, 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 and then I could have another C up here, like this, where you have H, 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 H. You could have something with a branch like that, or even you could turn this into a cyclic compound, C, 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 H, 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 H. And this is not all the possibilities. There are even more possibilities like that. And so the reason why I don't have any videos or anything talking about the Lewis diagrams of long molecules is because there's so many possibilities and you really need to know what the structure is ahead of time. And when you get into organic chemistry, you'll get into stuff like that. And so I find the value at the regular chemistry level of looking at these long molecules is really not important. All right, so another question. Would you say that if you use the formal charges to figure out where everything goes, yeah, that'd be a bad idea. I thought this was a random chem live stream. No, it's a class. No worries. Hey, class is over, and I don't have any class right now, so it's cool. No worries about that. And I get these questions all the time in my Lewis diagrams videos, and people ask me, okay, and they say, oh, that's the wrong structure of something, and that's because they might just follow and they try to make everything had to have 0 formal charge, which is really a bad way to go about drawing the Lewis diagram of something, okay? It works a lot of times until it doesn't work, okay? And so things oftentimes, like you've seen probably my example of, SO3 molecules, you can have a formal charge within a molecule. In fact, probably the simplest example of this would be carbon monoxide, right? Carbon monoxide is an example where you need to have formal charges on things, or else it's just going to be totally wrong structure, a terrible structure, right? Because the whole concept of the octet rule is more important than formal charges, hands down, in 99% of the cases, okay? And so for carbon monoxide, we look at this, we look at carbon. Carbon wants to make 4 bonds, all right? If carbon makes 4 bonds, it will it'll have a 0 form of charge. Oxygen wants to make 2 bonds. If oxygen makes 2 bonds, it will have a 0 form of charge. But you only have 1 carbon and 1 oxygen, so there's no possible way that carbon can have 4 bonds and oxygen can have 2 bonds. So we end up making a triple bond between them, and both of them have a lone pair, right? And in that case, the carbon is going to have a -1 form of charge, and the oxygen is going to have a +1 form of charge. But this is the best structure by far, because even though there are formal charges, everything has an octet and everything's happy, okay? And if you go through the process of how to do this, and if you go back to my original Lewis diagrams made easy, you can follow this and you can do the structure of carbon monoxide. And how would you do that, right? C has 4 valence electrons. Oxygen has 6 valence electrons starting off, right? Total it up, you have 10 valence electrons total, right? And so you start off and you say, okay, carbon and oxygen, there's no central atom. And so we're just going to put one single bond between them. The single bond is got 2 electrons. So we subtract out 2 and we're left with 8 valence electrons left over. And so I just put them in random spots, 2, 4, 6, 8. It doesn't really matter where you put them at this point in time, but you now have carbon monoxide there, and it's not happy. Carbon's not happy and oxygen's not happy. How do I know? Because neither one has an octet. Carbon has 2, 4, 6 electrons, not 8. Oxygen has 2, 4, 6 electrons, not 8. So we're going to take 2 electrons and a lone pair and turn it into a bond, and it's going to turn into C, double bond O, and you still have 2 lone pairs on oxygen. Now the oxygen's happy, right? The oxygen has 2, 4, 6, 8 electrons around it. It's happy, but the carbon's not. And if you stop here, this structure is not good, okay? Because this is a non-octet carbon, all right? And so we're going to continue on. Even though they both have formal charges of 0 at this point, it's still a bad idea to stop here because carbon is super unhappy, having only 6 valence electrons, okay? And so what I'm going to do is I'm going to take 2 electrons here and I'm going to turn them into another bond. So it's going to be C triple bond O. And that's that. Okay? All right. So I think I kind of ran out of space there, and hopefully that helps. And anyway, just for fun, hopefully you enjoyed that. And Louis here, awesome. My iPhone is running out of batteries and it's yelling at me, so I'm gonna have to stop here. And great to see you guys. How's it going, Louis? How's it going, William? Good to see you guys. Are you guys still in the US, by the way? I know a lot of you guys have been, a lot of my students have been traveling, going back home. But are you guys still here in the US? Just wondering. You don't have to comment. Anyway, my phone is, yes, you're all here. Awesome. Good to see you guys here, although I can't see you guys because we can't go to school. But hey, so if you guys are interested, William and Louis, if you guys are, almost all flights are canceled. Wow, that's crazy. If you guys are interested for my Bible class, rather than having a class, we're just going to have a Zoom meeting together. If you guys want to join us, you're welcome to. I can just add you into the Zoom meeting if you guys want to join us. And we're not really talking about anything serious. We're just gonna hang out and talk about stuff. So you guys are welcome to join us if you want. And you can tell me I got to sign out because my phone's dead here. But yeah, sure. All right, cool. So, and if anybody else wants to join, just tell them to email me, and that's cool. You guys can join. All right, so signing out here. Have a great weekend, everybody. Bible class is at 1:50. Okay, 1:50. So it's your block 8. All right, cool. Hey, Boren's here too. Hey, Boren. All right, cool. All right, see you guys.